Today we study ESA16H, trivial second-order differential equation. We recall the elementary differential properties of the exponential function whose derivative is identical to its original form. So we multiply dx both sides, and differential of this exponential function is exponential function multiplied by the differential dx. The initial condition for this function is exponential 0 to the 0 is 1. If we replace this x with ax, the form is the same. Now we can factor this a out to find this expression. We rewrite this one by dividing this identity by dx. So the derivative of exponential ax is identical to exponential ax, except that we have additional factor a. This can be obtained by using chain rule. And because of this, we can rewrite this one as an inverse transformation of the differentiation is integration. So indefinite integral of exponential ax is identical to 1 over a, the total differential of exponential ax. Because of this, as a result, we find that exponential ax is the integral of exponential ax is identical to 1 over a exponential ax. Hence, we can find that derivative of function is the same as itself, except that if I have a factor of a, then this function is a kind of an exponential function, except that the argument is replaced with ax. Here, c is a constant whose value can be determined by evaluating the function at x equals 0. Now, we know this is the first-order differential equation. That means the first-order derivative and functions, their linear combination has some relation that is called the differential equation. The first order means a maximum derivative is the first-order derivative in this linear combination of f of x and derivative, and their linear combination equals 0, for example. This is a kind of exponential, a kind of differential equation. Now, the simple case, this differential equation has a general solution such that the exponential ax multiplied by the arbitrary factor. What about the second order differential equation? Now, it can be expressed in terms of first order and another first order derivative of f. Now, we know this expression. So first order derivative gives a, and another derivative will bring in another factor a, so a squared multiplied by f of x. If this differential equation is identical to this, then it is true if a squared equals 1. The solution of this quadratic equation is a plus minus 1. Okay, so I can substitute exponential x for this f of x to reproduce this identity. And it is also true if I substitute exponential minus x for this f of x, it is true. What about the linear combination? Arbitrary number a and b are multiplied to the exponential, and this if I take the derivative, and this is minus BE minus X, and then if I take the additional, so second order derivative of this is first order derivative, and if I take another derivative, it becomes AE to the X, and this negative sign flips to return to the original value. So this is the reason why the linear combination of exponential x and exponential minus x is also solution of this. So general solution, arbitrary solution of the equation is this. We can introduce the hyperbolic functions. There's the even part of this exponential and the odd part of this exponential is called cosine hyperbolic and sine hyperbolic function. And we can express this linear combination of exponential x and exponential minus x as the linear combination of cosine hyperbolic and sine hyperbolic. Sure, the coefficient should be replaced with another independent one. Note that the power series expansion of the cosine hyperbolic and sine hyperbolic, we can reproduce this if I add 1 and minus 1 to kth power. They survive only if the power of x is even number. So cosine hyperbolic is an even function, and sine hyperbolic is, this one explicitly shows that it is an odd function. So we have odd powers in the expression. Number 3, we make use of the solution of the differential equation. We know the solution is exponential ax multiplied by the arbitrary number. What about this? Second order derivative plus f of x equals 0. That means second order derivative of f is minus f. Okay? So we know if I have this relation, we make use of this relation to find that it is a squared f of x. This means a squared equals minus 1. If a squared is minus 1, squared a squared equals minus 1, its solution is plus minus I. As a result, exponential ax and a equals plus minus I, we have two solutions, exponential ix and exponential minus ix. And their linear combination also satisfies the same differential equation. As a result, the general solution of the second order differential equation, this is a trivial one. This one is either exponential ix or exponential minus ix or their linear combination. The most general form is this. Again, just like what we have done with the exponential function, we have even part and odd part. And even part is cosine and odd part is a sine. Sure, this exponential ix, exponential minus x, ix, their linear combination can always express in terms of a linear combination of cosine and sine. Now we arrive at a point that it is an equation of motion for the simple harmonic oscillator. And actually, it is related to a mass spring system, spring constant K, and if it's equilibrium position where the spring force does not apply to the mass, and any deviation from this equilibrium position generates the restoring force to the equilibrium position. If it moves to the left, then the force is toward the center. That is the equilibrium position. So Newton's law of motion gives this MA equals minus kx. Force applied to this mass is proportional to the spring constant k and proportional to the displacement from the equilibrium position, and this negative sign stands for the restoring force is opposite to the displacement from the equilibrium position. Therefore, we arrive at an equation motion, and we divide both sides by the mass, and we have double derivative of x, and k over m, x equals 0. We know the spring constant and mass, both of them are positive, and the k over m can be expressed as a square of a real number. And this real number can be substituted for this k over m and equals to 0. We call this a characteristic frequency of the spring angular frequencies, characteristic angular frequency for this spring mass system. And this we call this omega is square root k over m. Now we can make use of the previous result for the case when omega squared equals 1 identity. Now the second order differential equation, solution for the second order differential equation can be found by trial and error. Exponential plus minus I omega t squared will bring in additional factor minus omega squared. Wait a second, there is exponential plus minus I omega t is missing. Hence, this is second order derivative. Double dot means a second order derivative of this plus omega squared equals 0. So this one is the e to the plus minus I omega t. Both of them are solutions of this equation, this equation of motion. And therefore, the linear combination is also the solution. In addition, both of them, exponential I omega t and minus I omega t, can be expressed in terms of sinusoidal functions. If I take the derivative, cosines becomes minus omega sine omega t by applying the chain rule, and the sine omega t's time derivative is omega cosine omega t. So using this, why don't we apply the initial condition, the initial position at t equals to 0, sine disappears and cosine becomes 1. If I substitute 0, then it is a d1. D1 represents the initial position. And what about the first order derivative evaluated at t equals 0? Then we have omega d2. So omega d2 is the initial velocity of the mass. Therefore, d1 is identified. d1, the coefficient of cosine, is identified with the initial position, and d2 is x dot evaluated at t equals 0 divided by omega. So this is the final result. So first, we can introduce undetermined arbitrary parameters as a coefficients of each solution. In here, we have second order differential equation. We have two linearly independent solutions, and their coefficients can be determined by the initial conditions. And because we need the two independent solutions, we evaluate, for simplicity, evaluate the position and we don't have to compute the acceleration. We evaluate the velocity at t equals 0. So using these results, we can determine the undetermined coefficients to find a value of x of t at any time. That's it for today. Thank you.